This is a great question on tiling. We're just given this one rule that we have to follow. So when two tiles meet, the two regions must be different colors. One will be black and one will be white. For part one, we're going to make sure that the top left one is A. I'm just going to shade a few grids in, and we're interested in the different grids that we can obtain. How many different ones can we obtain? So I'll just use a different color for the ones that I'm adding. Well, I could definitely put A in. That would be an option. So that, but I could also put D in. So basically, there's going to be two choices for the top right. But if I look at the bottom left, there's also going to be two choices because I could put A in or I could put C in. So if I draw another one here, right, with the same top right as the first one, but now I'm going to put C in, then I can see I'm going to get four options actually for top right and bottom left. Because I'm going to get the same down for the second and fourth ones. I can either have A or I can have C. Okay, great. Four options so far. However, for the last one, what I see is that the bottom right, I don't have any choice. I'm going to have to make sure that this is black like this because the left has to be white, but the top has to be black. I'm just using a red color to kind of identify what bit I'm working on. And then over here, that is going to have to be white at the top. That's going to have to be black. Then this will have to be black. And then I'm going to have to go with that as black. So as long as I explain this, I can say that there's four ways. And this is meant to give insight into what is going to become a more complicated problem in a minute. And the key idea I just want to highlight again is that there were two options for the tile to the right, and there were two options for the tile below. That's how I ended up with four, because it's 2 times 2. And then the bottom right one was dependent on those two that I put in, so I didn't have any more choices from after I put those two in. That was actually one part A. And part B, the statement I just made is going to be really useful. In how many different ways can a 2 by 2 grid be covered by 4 tiles in total? So the top left now is going to have 4 options. And after we put that in, the top right, whatever tile we have, is going to be 2 options. Just like we saw in the original grid. And also, the bottom left will have 2 options. Let me just give a little picture to kind of convince you of that. So I've just drawn a rough grid now. Okay, let's say I start with this tile here. Then I could either here put this tile, or I could put it would be this tile. And then down here, I can either put this tile or this tile. So that's what I mean. I've got my 4 options here, but after I put one in, whatever the tile is, there's going to be 2 options here and 2 options here. But after I put them all in, let's say I go with this and then maybe this, and over here I go with that. In fact, there's only one option for the bottom right. Then bottom right only has one choice. So there are 4 times 2 times 2 equals 16 ways of, how do they say it, of tiling the grid. I'm just going to write of tiling. It makes sense really. Like, there's nothing special about that tile from part 1A. Okay, I had 4 there, so if I swap it around, surely I'm going to get 4 for that lot, and then swap it around again, I'm going to get 4 for each one. But I've tried to show like comprehensively why by explaining that there are 2 options and 2 options and then 1 option. So 16 in total. On to part 2. Right, this is getting going now. And how many different ways can a 3x3 grid be covered by 9 tiles? So obviously, whilst you could have got away with the earlier parts by actually drawing them all, it's going to suddenly get a lot more difficult. And you can see the next question is to generalize it to n tile, n by n square. Okay, so this is, sorry, is this part B? Part 2. Okay, well, I'm first of all going to start with the grid and just get a bit of a feel for it. So there's going to be 4 choices for the first tile. Let's say I go with that. And then the one on the to the right of it, I could either go with that, or I could go with that, same tile. So there's going to be 2 choices for that one. And then it's going to work out in the same sort of way. Actually, I might just change it to that. There's going to be 2 choices for the top right. In fact, it might be good to make a little grid and basically write down the number of options for each one as I go. Remember, we're timesing them. And then just like before, there's going to be 2 choices for the one below. I can either go with that one or the same one as before. But now, when I get to here, I have to go for this one here. So there's only 1 choice. And the same applies here. I'm going to have to go with that one. There's only 1 choice here. Right, back onto the bottom left, actually, there's going to be 2 choices again. So I've got freedom. There's nothing restricting me to the left. It's when I'm already connected to 2 of the squares that I don't have any freedom, which is then what is going to happen with the remaining 2. I'm going to have to go with that one. So there's going to be 1 choice. And then it's going to be this one here. So there's only 1 choice. So as long as you can explain that in the words, then, I think we'll be okay. There's going to be, oh, sorry, I stopped multiplying as I went, but 4 times 2 times 2 times 2 times 1 times 1 times 2 times 1 times 1 is actually going to be 4 times 4 times 4, or 4 cubed, or 64 ways. So as long as you write some words down and explain this clearly, that is a good solution. Just for info, another possible solution would be to say that there were 4 here, and then just jump in and actually say that there's no restriction here. There's 4 options here and here as well. But once you put those in, then there's going to only be 1 choice here, and then 1 choice here, and therefore 1 choice here, 1 choice here, whenever there's like 2 either side, 1 choice here and 1 choice here. So this is another way of showing that we get 4 to the 3. But I wouldn't have thought to do that. I just kind of saw it in the answers. Finally, let's generalize this to an n by n grid. So here there's going to be 4 choices for the top left. And then 2 choices for remaining cells in the top row. So this will leave us with 4 times 2 to the power of n minus 1, because we've got remaining, I should probably say the remaining n minus 1 cells in the top row. So this is the first cell, and then it's 2 for every other one. So in total, there'll be n cells. Brilliant. And then what we're going to have in the one below, or actually what I should really be thinking of, is I've dealt with all of these. And now it's all about down here because I get two choices. But once I put this one in, then this is fixed with 1. These are all 1s, but I've got two choices here. So we're going to have another 2 to the n minus 1. I should probably, okay, let me just say this again. Remaining cells, or the remaining n minus 1 cells in the left column will also have two choices each, which will give me another 2 to the n minus 1. All the rest will have one choice. Therefore, it's going to be 4 times 2 to the n minus 1 times 2 to the n minus 1 ways of tiling. This becomes 4 times 2 to the... we can actually add the powers here. This is a little rule of indices. So if you ever have, say, x to the 5 times x cubed, we actually get x to the 8. You add the 5 and the 3, because we're actually timesing 5x's together here. And we're timesing 3x's together here, so it makes sense that overall we're timesing 8 of them together. So I'm going to get 2n minus 2. Now 4 is actually 2 squared. So I can write 2 squared times 2 to the 2n minus 2. And as I just did a second ago, I can add that on. And then these cancel, leaving a really nice simplified answer. There's actually 2 to the power of 2n choices. The other way that we could do it would be to come back to here. It is a nice approach, and just say along the diagonal, there's going to be 4. So it's going to be 4 to the power n. And yeah, that's quite a nice way of leaving it actually, or then rewrite it as 2 to the 2n, because this is 2 squared to the n. Another rule of indices says that you can then multiply these. For example, if you have x squared cubed, you're basically doing x squared times x squared times x squared. You're timesing 6x's together. This gives x to the 6. So you can use that. All right, big fan of that question. Really nice question on tiling. Proper challenge, but it gives a lovely result at the end. Well done. Thanks for watching.